So we're going to do Physics 6.2, Newton's Laws topic test. Newton's laws of motions are important in the way rockets move. Tick the box with the correct statement. So we're looking for Newton's third law. It can be written as unbalanced forces change the motion of an object. That kind of refers to Newton's first law, where a balanced force, something like I often use the belt. If it's not moving, or if it's in constant or uniform motion, then the forces are balanced. Okay, so if I was to do a side view of this, the size of the arrow going down should be the same as the size of the arrow going up. If there's the weight is 700 newtons, weight is mass times the acceleration of gravity, remember. Then there's going to be, I think I said 700 newtons there, didn't I? 700 newtons going up, although that would have to be a heavy bell for it to be that size of force. So it's not the first one where it says unbalanced forces. I mean, unbalanced forces do change the motion of an object, but it doesn't apply to Newton's third law. Now, the forces of two objects on each other, action and reaction, are always equal and in the opposite direction. That is Newton's third law. So that's why I've ticked it. And then the resultant force is equal to mass times acceleration, FMA. It's true again, but, you know, it's his second law, so it's not his third law. A rocket exerts a force of 15 million newtons on hot gases, which exert a force of, well, remember now, they've got to be equal in the opposite direction, so they've got to be the same. So 15. Not less than, not more than, the same. The diagram shows the direction of the force produced by the rocket. So it's going down, okay? And he wants a reaction force now. And an arrow in the diagram direction of the force of the hot gases on the rocket. So the hot gas is pushing up on the rocket. Okay, ideally I would have drawn it. I would have drawn it there, but then, you know, there's always that worry that they're not going to see the arrow. Again, here would have been okay, but you're going into your text. I've just done it on the side. Do not do it on an angle, okay? You will not get the mark for that. It's really common. Just be very, very neat on that. Even that is, you know, I should have drawn it with a ruler and a pencil, really. A model rocket has a weight of 5 newtons, an upward thrust of 20 newtons. Now you can see I was already in the mode writing down what I've got, ready to use a formula. I was going to use FMA, but it's given me 2 newtons, 2 forces. It's given me weight and it's given me force. So there's not a formula I can use for that. So I'm going to have to use the resultant force thing, whereby, if you think about it, it's got a weight of 5 newtons. So just drawing a little diagram there. It's got a weight of 5 newtons. But it's got a thrust, which is going up in the opposite direction, of 20 newtons. So the resultant force is the difference between them. Okay? So I've just taken 5 from 20 there, and I've got 15 newtons. That's the resultant force. If they ask you for a resultant force, and they've not given you mass or acceleration, but they've given you 2 forces, that's going to be the one. Often you'll see a diagram, and they'll say, what's the resultant force here? Again, don't concern yourself with formulas. Just think of it very simply. The resultant force is, if it's moving in one direction, that bigger force is going to be, so you're going to take the smaller force away from the bigger force. Now, the mass of the rocket has 0.5 kilograms. Use your answer to calculate the acceleration. So we've got the resultant force, and we've got the mass now. So they've given you the formula there, but if you didn't and you had to refer to the first one, if you're looking for your acceleration this time, I cover A, it's going to be F over M, so 15 over 0.5, gives me 30 meters per second. For 2 marks, I think that is a lush question. A bit more practice here on time velocity time graph, sorry. A train of mass 8,000 kilograms leaves a station A and arrives at another station D. Its journey is shown by here. Describe the motion from A to D with as much detail as possible. Now, it's worth 3 marks. You can calculate the accelerations for 3 marks. I'm just going to go with the 3 steps from A to B, from B to C, C to D. So from A to B, the train accelerates and I've missed that. So I should have said from A to B, train accelerates steady. It's a steady acceleration. It's not an increase in acceleration or a decrease in acceleration. It accelerates at a steady pace for 200 seconds until it gets to 25 meters per second. Then, from B to C, it stays at 25 meters per second. So if I get a ruler, just show you each square is worth 1, so that is 25 there. And it stays there for 1 to 300 seconds, or you can say 500 minus 200, so 300 seconds. From C to D, it decelerates steadily from 25 meters per second to 0 meters per second in 100 seconds. So this one has a faster, it's decelerating faster, or you can say it's decelerating faster than this one's accelerating, because you can see it's got 200 seconds there to get to 25 meters per second. There's only 100 seconds there to get from 25 meters per second to 0. Not that it's asking that, but it might be just worth highlighting that. The line is steeper on this one than that one. Use the graph and the equation from page 2, so it's not giving us an equation now, to calculate the resultant force. So we need a force acting on the train when it's accelerating. So I've got FMA. Now I know my mass to be 800 kilograms, so I know my mass. I'm looking for my force, but I don't have an acceleration. So I need to calculate an acceleration. To do that, I use this formula down here. Final velocity minus initial velocity. Again, this is found in the front of your books. Over AT, acceleration in time. So I'm looking for acceleration. To cover A equals V minus U over T. My initial velocity, remember this is from my acceleration. My final velocity, which is V, is 25 meters per second. My initial velocity is 0, so 25 minus 0 is just 25, over the amount of time it takes me, which is 200 seconds. So it's going to be 25 over 200 gives me 0.125 meters per second squared. Now I've got my acceleration. I can put this back into this formula now. If I'm looking for force, it's going to be F equals M times A, and you're just replacing them. So 80,000 was my mass, and then I've got my speed there, and it comes out to be 10,000 newtons. A lot of work there for their marks, in my opinion. When you think of that other question that was worth 2 marks, and you only had to do a simple calculation. Bearing in mind, write everything down. When you're doing these calculations, don't think, oh, I'm clever, I can do it in my head, I've carried this equation on. Okay, unless you're showing all that, it's unlikely you're going to get full marks. Okay, show them what you've done. And even if you get one figure wrong, so let's just say that I plugged that in wrong to my next formula, you're going to get a mark for carrying on. Explain how the size of the resultant force acting on the train during acceleration compares to the answer in... Oh, right, so we do get that question now. So what that question is saying, how does this compare to that? So during deceleration, well, the force is bigger because the time it takes is half. You can see that there. So it's 200 seconds there, only 100 seconds there. And it's got a steeper gradient. Okay, so that's the things you can tell. There it's got a bigger force. It's got a steeper gradient, and it usually covers less, the same distance or the same speed in less time. And now this is for higher only, use the graph and the equation to calculate the distance. Now the distance for this would be the area underneath. Now we're not going to spend a lot of time on this because it's not foundation, and really this is this is part of your math skills, your numeracy skills. But to get the area, I've split it up into 3 sections. I've got the box there, so if I know my area is going to be this side times this side, well, this side is 25 meters per second, and this side is going to be 300 seconds. So you can see that I've just plugged it in there. So 300 times 25 gives me 75,000. And then for a triangle, I just half that area then. So I've said 200 times 25, 100 times 25. I'll just show you there. So it's 200 times 25 times half, and then 100 times 25 times half. And that's where I've got that distance from. Okay, add them all up in the end, and I get that distance. And use your answer and equation from page 2. Calculate the mean speed of the train. Well, this is just a distance, speed, time, because we want speed. I know my distance from there. I know the time it takes me, so I'm just putting S equals d over t, which comes out to be 18.75 meters per second. And this is a higher question. This one is not going to be relevant at all in the exam, but just for your peace of mind, that P plus R, the area there, is going to be equal to your Q there. But that is very unlikely to come up in your exam. Question 3 then is plot the journey of the car shown below. So, part of the journey of a car is shown below. Using information on page 2 to calculate the total distance. Again, it's one of those distance ones where you're calculating the distance under. There's the calculations. I'm sure you could do that if you press pause. Let's see where I've got that from. But I'm going to concentrate now on this 6-mark question because I see the time is already up to 11 minutes. The passenger in the car has a mass of 70 kilograms. That's going to be pay a factor. That's important information. Discuss how the resultant force of the passenger changes throughout the 80 seconds of the journey. So we're referring to this graph here. Include calculations. This time I'm going to do the calculations because it's 6 marks, and explanation of how the resultant force, whether it's going forwards or backwards, that sort of thing. So the direction of the force. So I said in the first 30 seconds, the resultant force is going forward. Well, it is in the first 30 seconds. Now I can calculate that acceleration as well, because I've got an initial initial velocity and a final velocity. And you can see I've done that there. So I've said my acceleration is 60 over 30, which gives me 2 meters per second squared. And then I can actually calculate the force because I know my mass. So my force is going to be 140 newtons in a forward direction. Then I've said between 30 and 65 seconds, the speed is constant at 60 meters per second. Well, it is. It's a nice flat line. It's not increasing acceleration anyway. It's just gently bobbing along for 65 minus 30 is 35 seconds at one pace, which is 60 meters per second. For the last 15 seconds, there is a resultant backwards force, or you could say opposite direction force, causing a deceleration. Now this force, I can already see it's a bigger force because it's a steeper line, but I'm going to calculate the force anyway. First I need to do acceleration. To do that, initial velocity, which was the final velocity, which is 0, and the initial velocity, which is 60. So there's my initial, there's my final. It's just going to come out to be a negative number. Actually comes out to be negative 4 meters per second. If I plug that now back into this formula, I've got my mass, use the same mass. It's going to be 70 times 4, which is 280 newtons. So, it's double the force. It's double the force. Bigger force decelerating and accelerating. That should get you 6 marks.